At the top of the Australian Alps is a tiny working gold mine. The Red Robin's gold has kept Ken Harris going for 34 years. Hello, Ken.
G'day, Clive. Just mind your head on those stoles when you're coming up. There's not a lot of space here, as you can see.
I've come here to see the geological structure that contains all the gold-bearing veins. It's called the Red Robin Fault.
You can see here, that's quartz right away across there, and that's sort of that's the footwall, and there's a hanging wall, and just take the quartz out, and then every now and again it'll narrow in.
I've come because I want to explore why faults and veins so often go together. So I'll talk to Ken and one of the world's top academics in the field.
Well, originally the reef outcropped on the surface. It was a quartz reef, and basically I've just sunk down on it more or less the whole distance. But to make sure that it's got gold in it, you have to take samples to check for gold, but basically it comes down to following the quartz.
This quartz lies along a steep fault, which extends from the surface about 100 metres above us to at least 20 metres below. And like almost every gold mine, if there was no fault here, there'd be no quartz and no gold. Ken struggles and squeezes to find the gold-bearing quartz. His work slowly reveals the path that gold-rich fluids once followed. But the fault is not as simple as it seems. The veins pinch and swell, and their complex shapes show that fluids invaded the fault repeatedly. But even complex systems can make sense when you understand the different elements at play. One scientist who understands these elements more than most is Professor Rick Simpson. He realised a key to understanding the relationship between faults and quartz veins is earthquakes.
Because one thing we know now is that, faults mostly move during earthquakes. It's actually quite rare around the world for a fault to move steadily and not in jerks during earthquakes.
Rick came to study earthquakes by chance. In the 1970s, he left New Zealand to study for a PhD.
So I ended up in Scotland working in the Outer Hebrides, where there was an ancient fault zone that had been neglected because it penetrated some rather uniform rocks, the Lewisian gneiss, and you couldn't make an ordinary sort of geologic map. But what I realized you could do was map bands of different types of fault rock, the products of fault movement, and a pattern came out of that.
It was common back then to picture faults as slow, creeping structures. But Rick found evidence that some faults had moved very rapidly.
And that made me realize that the rocks held clues as to what does go on during an earthquake. But as a geologist, I became aware that quite a lot of faults that we routinely map have some sort of hydrothermal vein material along the faults, and sometimes it's calcite or quartz or gypsum. But one of the characteristics is that there is textural evidence that this material was not all deposited in one episode, but it came in a series of pulses of fluid. And the natural thing was to say, well, perhaps this incremental deposition is something to do with incremental displacement on the faults. It's tied in to earthquake slip episodes.
Rick realised that to fully understand the vein-earthquake relationship, he had to factor in something else, that earthquakes behave differently at different depths.
For much of the Earth, earthquake activity is in the top half of the crust. It only goes down to about 15 kilometres, maybe 20 kilometres, and then it stops. And so as a fault zone goes from the top to the bottom of the crust, it changes from being brittle or frictional to being more ductile and flowing with depth. But one of the fascinations about Victorian gold and the other orogenic gold deposits is that they have formed probably mostly in the range of sort of 7 to 15 kilometres, something like that.
But at these depths, the pressure of overlying rock is enormous, and horizontal compression or shortening is often an additional force in active orogenic terrains. So how can vein fluids enter fractures and faults under these extreme conditions?
Here the rocks are being squashed. So it's counterintuitive, isn't it, that
It's totally counterintuitive.
that you would
yes.
get veins?
Yes, and in fact you see huge vein systems localized on pretty steep reverse faults in these zones of compression. And it raises a very interesting point. You say, why on earth would you get hydrothermal deposition, which involves the creation of space, on a fault almost perpendicular to the shortening direction?
So what's the key to understanding that?
To create space at depth, you have to counteract all the overburden pressure with abnormal fluid pressure.
The huge weight of overlying rock keeps fractures tightly sealed, but if gold-bearing fluids become highly pressured, they can literally pump open fractures and faults, and the fluids will seek the fractures that require the least pressure to open.
One of the attributes that's notable about these orogenic gold deposits is that you see quite a lot of flat veins associated with them, some of which have beautiful fibre structures. They've opened vertically, and in simple mechanical terms, the only way we can really understand this is if we have a fluid pressure driving crack opening that is counteracting the overburden pressure. And that requires very high fluid pressures.
The overburden pressure is a force to be reckoned with. The vein fluids had to counteract it, and it's now the same for Ken. He needs to keep the fault from collapsing using closely spaced timbers.
There's not enough room for rock bolts here, hardly enough room to use a rock drill, so I just put in these timbers. You call them stulls, so you have to cut a hole in the footwall, so a toe for the stull, measure it accurately and just slam it in with a 7 kilo sledgehammer and put in the wooden wedges as extra support, but it's got to be tight, otherwise the whole thing can fall in. You're always checking it, sort of see. This is reasonable the way I've got it at the moment, but it's pretty loose overhead, so just sort of proceed with caution. I'm due to put in another stull just there, actually.
Ken has only 100 metres of rock above him, but when the veins formed, there may have been kilometres of overburden. This weight is called lithostatic pressure. This is an immense force, but gold-bearing fluids released during metamorphism can counteract it and form veins. Nearer the surface, it's more likely that hydrostatic pressure prevails. This is basically just the weight of the water itself, and is much weaker than lithostatic pressure at depth. Rick realised this was a very significant difference, and from there developed his fault valve model.
So the notion is that if you can make a link between these two zones, suddenly a fracture permeable pathway associated with the rupturing of a fault, then you're likely to get discharge along the fault from the area of abnormal overpressure back towards the hydrostatic condition.
So faults can act like fluid valves. Fluid pressure rises below a zone of impermeable rocks near the base of the seismogenic zone. If a fault ruptures the impermeable seal, overpressured fluid can escape into the hydrostatic zone above. This drop in pressure creates ideal conditions for vein deposition.
And what we would suggest is that there are endless cycles of fluid pressure accumulation somewhere around the bottom of the seismogenic zone with episodic discharge through the faults every time they fail during an earthquake.
Each earthquake is a potential vein-forming event, so vein textures are good evidence for this cyclic behaviour.
You can see when you look at a vein like this that it's composite, and I can see probably at least a dozen episodes in there, but microscopically you could probably find even more episodes of fracturing, hydrothermal deposition, refracturing, and so on.
By the late 1980s, Rick's interest in veins led to a serendipitous meeting with Canadian gold experts Howard Poulsen and Francois Robert, which led him to fully develop the fault valve model.
And then we were sitting in a bar in a place called Fort Francis, watching ice hockey and discussing mesozonal vein systems. And Francois was drawing sketches of sigma mine on beer mats. It was a wonderful evening. It was one of those evenings you remember as a scientist all your life because everything suddenly clicked. And you had the flat veins, you had steep reverse faults, and I said, hang on, what's the angle between the two? And it turned out to be 70 degrees. And I said, but that means it can only move if it's wildly overpressured. And that was when valving really took off, because we sort of saw that you need this rather exceptional combination of circumstances. I mean, I look back to an undergraduate lecture. Our lecturer said, the thing to remember is it takes a lot of coincidences to make a mineral deposit. It's never one thing. And trying to identify those coincidences is very interesting.
You've alluded to the fact that you've got high fluid pressure and the steeply dipping fault, but exactly what is the significance of that relationship?
Well, it comes out of some pretty basic mechanics, and you can actually do the algebra on an envelope. But faults are easiest to move when they are aligned at about 30 degrees to the compressive stress axis. And in a compressional regime, that's horizontal.
So that's an angle, something like that?
Yes. And we see an awful lot of thrust faults that are active at dips of about 30 degrees. But if you look at the global distribution of active reverse faults, we see that there is in fact a range that goes from sort of 10 degrees up to about 60. And we don't see any reverse faults active at steeper than 60 degrees in terms of modern earthquakes. And the significant thing about that is that it turns out from the algebra that if the easiest orientation to make a fault move is 30 degrees, then the frictional lockup angle, beyond which it's extraordinarily difficult to make a fault move, is 60 degrees. And there is a condition, if you have fluid pressures a little bit more than lithostatic, that you can actually make a fault move when it's 60 degrees or more. And that's what you seem to be seeing in a lot of these deposits.
So the key relationship is that if you raise fluid pressure enough, presumably with some seal capping the fluids, that even a steep fault that normally could not move will move.
Provided there aren't any better oriented faults in the neighbourhood.
Okay.
And that's a key issue, because if there's still a favourably oriented fault, that will go in preference.
Rick has shown that if gold-bearing fluids exert enough pressure, they can force their way into faults and fractures, even very steeply dipping faults. Most of all, Rick's work shows that veins formed in very active fault systems.
I think that's one of the exciting things that we're seeing, is that the structures weren't dead when the fluids were moving around. And that's something the old-timers knew very well. They comment on it again and again in the old mining literature of the 1890s, 1920s. They say, look, it's clear that these structures were active when the hydrothermal fluids were moving through them. And it's true. And that's exciting.